Hello everyone, welcome to Velotio Tech Shorts. My name is Sandeep Chauhan. I'm part of Velotio software development team. I specialize in building big data pipelines and solutions for real-time analytics. And today we are going to discuss about how we can use Apache Flink for real-time analytics. Is the agenda for today. We'll discuss about what makes Apache Flink better than its alternatives. We will discuss about internal working of Flink, which means we'll be talking about the life cycle of a job submitted onto the Flink cluster. We'll talk about anatomy of a Flink program. This will basically discuss about the developer's perspective of Flink program, and we'll talk about Flink's fault tolerance mechanism and scalability. So in this slide, we'll talk about what makes Flink the best among alternatives. So Flink is designed to process data streams at high speed, making it suitable for handling huge volume of data in real time. It has built-in fault tolerance capabilities, which means it can recover from failures and continue processing data streams without losing any data. It is designed to scale horizontally, meaning it can easily handle increased volume of data by adding more machines to the cluster. It is able to process data streams with a very low latency, making it suitable for applications where quick processing is important. It supports processing both stream and batch data, making it versatile choice for a wide range of use cases. Moving on to the next topic, the internal working of Flink application. So Flink is a distributed system. It works by distributing the workloads to multiple nodes. Hence, it requires effective allocation and management of computing resources. The Flink cluster has job manager and multiple task managers. The job manager submits parallel instances of the job to the task manager and manages the resources. Flink can integrate with most of the common cluster managers like Yarn, Kubernetes, Mesos, and standalone cluster. So let's discuss what happens when we submit the Flink job to the cluster. The main actor here are client system, the job manager, and the task manager. The client system can be the CLI of your local machine or the CLI interface of one of the nodes in the cluster where we submit the command to run the Flink application. When Flink application is executed, it creates the job graph, which is submitted to job manager. The client system can detach itself from the cluster or remain attached to get progressive reports of the submitted job. So here is an example where you can see how we write the code and how the job graph is created out of it. So as you can see in the source code, we are connecting to the source, which is Apache Kafka. We are performing map transformation, window transformation, and keyby. Then on the data that we have transformed, we are sending it into the sink. So this is the destination where our transformed data should go. So as you can see, there are 4 nodes in this graph and an edge that denotes the data flow. So once the job graph is submitted to the job manager, based on the number of resources it has, job manager will create that many parallel instances. We can also set the parallelism in the Flink code. So for example, as you can see in the right, we can see the job graph that is submitted to the job manager. And let's say the available parallelism is 2. So the job manager will create 2 parallel instances of this job graph, and which is also called as execution graph. So there are 2 execution graphs, and these parallel instances are submitted to the task manager for running the job. So next, the parallel instances are submitted to the task manager. So for example, we had a job which connects to the source, performs some transformations, and then send the data to the sink. But now you can see, based on the parallelism, which is equal to 4, the 4 parallel instances are created, which are called as execution graphs. So 4 execution graphs, and each execution graph is submitted to 1 task slot within the task manager. Now, task slot is a basic execution unit within task manager. It can be a core of a processor, or it can be 1 thread running on 1 core of a processor. Once the job has been executed, the task manager send the signal to the job manager saying that the job has been completed. And this is how the execution of job takes place on the Flink cluster. Let's now take a look at a Flink program from developer's perspective. Here are some steps to write a Flink program. So first we get an execution environment to initialize our code. Then we connect to the data stream, we perform transformation and specify where we have to send the data. Let's talk about what transformation we can do in Flink. There are many, but I'll demonstrate a few of them here. So the first one is map. It takes one event from the stream at a time, performs some modification on it, and emits the modified output. So the output can be of any type. So for example, in the left, you can see we are taking an integer and we are returning a string. So it takes an integer, it convert it into the string equivalent of it, and it emits this in the output stream. So for example, as you can see, the number 89 and its string value in the output. So let's move on to the filter operator. We'll take one input from the stream, perform some condition check, and then return the event for which the condition turns out to be true. So for example, let's say as an input, we are giving the number from number 71 to 100. It will perform a condition check whether that number is an odd number or an even number. If it's an odd number, just emit that particular event in the output stream, else just skip it. So as you can see, all the even number can be seen in the output stream. So next is the reduce. Reduce will perform aggregation on the input stored in the window. Now, for example, you can see that we have total of 12 elements in an input, and we have applied a count window. Whenever there will be 3 elements within our count window, we'll perform aggregation on it. Basically, we'll just sum up everything and then we'll return it as an output in the output stream. So you can see for the first 3, we are getting the output as 275, 261, then 261, then 254, and so on. Next is a key by operator. So often at times we would require to perform aggregations on the data based on the key. So that is when we can use key by operator. It splits the single stream into multiple streams based on the value inside the event called key. So for each key, there is a separate stream. Event with the same key will flow through its designated stream. So for example, you can see E1, E2, E3, E4, E5, and so on events coming into the stream. And let's say we have applied key by on this event name. So there's a dedicated event stream for E1, E2, E3, and so on. Now let's discuss about Flink's fault tolerance capabilities. Flink has built-in fault tolerance capabilities. It can recover from failure without any loss of data. It uses checkpointing and stream replay mechanism to recover from a failure. Checkpointing will save the state of operators in the configured state backend. Now, state backend is a durable storage that we have configured while setting up a Flink program. Whenever Flink application is restarted after a failure, it will use the state saved in the state backend to restore the operator states and start to read the events from the offset that is present in the checkpoint data. So now let's talk more about the checkpointing. As you in the diagram to the left, you can see there are events flowing, and there is special event that flows along with these events into the stream, which are called as checkpoint barriers. These checkpoint barriers are important because they mark up till what data has been sent till that point in time within the stream, and what is the offset within the stream. So this is important because it helps the operator to know what was the state till that point in time. So this is what the checkpoint barrier does. Now let's see an example how these checkpoint barriers help the operator save their state into the checkpoint database. So depending upon the operator type, the data stored within the checkpoint data base is different. So for example, we have 4 data sources. Each of them are reading from a specific offset within the event stream. So whenever all the barriers arrive toward the data sources, it will save the offsets. And here are the transformation operators. So whenever all the input streams will give the input barriers, event barriers to them, the data that is stored within that operator is saved in the state backend, and in the checkpoint table, it will return the pointer to the state or the snapshot of data that they had before failure. And these syncs will eventually mark this checkpoint as completed when they have received all the barriers from their input streams. Now let's talk about, once the state is saved, how we can recover from the failure. So let's say during the recovery, the Flink program will select the latest snapshot from the state backend, and it will reset all the operators. For example, if it's a source operator, it will start reading from the offset given that is saved within the snapshot. If it's a transformation operator, it will load all the data that is present in the state backend as a snapshot, and it will start executing the application again from that point in time. Now let's talk about scalability. So we can horizontally scale a Flink cluster, and we can also scale it down. So this can be done manually. We have to trigger a save point. A save point is nothing but a manually triggered checkpoint. So we save the state of all the operators within the database. Then we add or remove the nodes for scaling down or scaling up our Flink cluster. Then after that, we reload the data from the save point into all the operators, and then we start the job from that particular save point. So these are 3 steps that are done manually. Then we have reactive scaling. So this is a feature of Flink which is only present in standalone cluster mode. So reactive mode configures the job so that it uses all the available nodes that are present in the cluster. So it's simply like when we add a node to the cluster, it will scale up. We'll remove a node from the cluster, it will scale down. So basically the difference is that we do not have to manually go through these steps. It will perform these 3 steps automatically. But the downside is that it will stop your running job, and restart it again from the point of failure.